Good morning, afternoon, or evening to everybody out there who's watching this. My name is Brandon Botzer. I'm a member of Team 2 for the Foundations of AI for the spring of 2022. My teammates here are Nick and Ambika. We, for this class, decided to take a look at Tic-Tac-Toe as our game. And within that, we set off to try to make an AI so that Tic-Tac-Toe could be flawless and always victorious, or as close to it as possible within this world. So without further ado, let's get into this. Let's talk about what we did, what we kind of looked at, what our results were, and see where this goes. So in a generic tic-tac-toe game, if you're familiar with it, you have a 3x3 board, and you are trying to line up 3 in a row of either X's or O's, or as they say in England, crosses and knots. And you can do this either going horizontally throughout the rows, or vertically through the columns, or diagonally through the main diagonals. So if we kind of take a look at what we have here, you could run this across, or you could run down, or you can go through one of the main diagonals, in all these different positions. So with a 3x3 board, you've got 1, 2, 3, 4, 5, 6, 7, 8 possible victory conditions there. That's the classic 3x3 game. We also decided to take a look at 5x5, 6x6, 7s, 8s, 9, and 10x10, so much larger board sizes. And in these larger board sizes, we decided to actually force the player to line up 5 in a row, 6 in a row, 7 in a row, 8 in a row, 9 in a row, 10 in a row. And this led to some kind of interesting responses from both the player side and the computer AI side of things. Before we decided to have the entire rows or columns or diagonals to be filled, we were actually looking to implement kind of a need to win condition. So let's say you were playing on a 6x6 board. We were originally looking to say, like, what if you only needed 3 to win on that board? But this is kind of a trivial thing to solve out, and it made some weird things happen. So we kind of got stuck with that, and we just kind of scratched it for a little bit. But we are looking at 5 to 10s for all of this in this problem space. So it's a really, really interesting thing. And in theory, you can make this larger and larger and larger to whatever board size you want. But in doing so, things get a little bit more time consuming, to say the least, as we'll see later. So when we have this 3x3 game and we're playing on these square boards, that means we're always 3x3 or 5x5 or n by n. It's a square grid. It's a square board. We're not playing on anything rectangular or some funky shape that you've come up with. We are trying to just figure out who can make their markings in that horizontal, vertical, or diagonal row. And that's really what we considered here. So in getting into this, there were a series of things that we went down, but our general solution follows the following procedure. We look for forced moves that the computer has to take, or else the game will end. And what we mean by this is, imagine a 3x3 game here. Okay, and let's just kind of set up a little board. So, you've got X is played twice and O is played twice. So X is up to play again. Here, let's put X. Let's put this one somewhere else. So if X is up to play again, where must X go? Well, if X is going to play again, X has to play here because that's a win. Way to go, X. That also is a block. But, if we have a slightly different scenario where, maybe O has played twice, X has played once, where must X go now? Well, X has to play here because if they don't, they're going to lose the game. So these are forced moves. It's a series of first-order logic of saying you have to play here. You have no other options. If you play here, you win and you're victorious. If you don't play here, as in the second case, you lose. And you can't have that happen. So this is a little implementation of a first-order logic in order to get the game to run a little bit faster. And we actually added that much later into this coding process here. The backbone of our work, though, dealt with or the miniMax algorithm. That miniMax algorithm, it's using a depth-first search in order to dive down the search trees, and it's trying to pull back from it ending conditions from those leaf nodes. So for us, one of our sides from the min and the max is trying to minimize the score. Classically, if you're reading the book, this would be like a -1 value. The maximizer is trying to +1 value. And then in our case, if we had a tie, we just called that a 0. And that's what we implemented kind of early on. We've also implemented some alpha beta pruning, which is the miniMax AB. This allows us to take a look at those final leaf nodes, figure out what they are, and then when we look into the future, we can recognize that we're not going to get anything better or worse, depending on, if you're the min or the maximizer, and just kind of eliminate those future branches. And we've even gone so far as to implement a depth limited search. And these pieces right here, they were all added after we kind of got the min-max algorithm working, as well as the forced moves, to try to speed things up because things were kind of moving a little sluggish, and we'll see that momentarily. But these are the 4 pieces of the algorithm that we've kind of implemented: forced moves, the minimax, alpha beta pruning, and the depth limited search. Now, when we initially wrote this, we had a naive minimax, and we got it working, and we wanted to test it first. So we said, let's just test it on a 3x3 board. That's the first non-trivial case. So when we test it on the 3x3 board, we get it to work. It takes a few seconds for the AI to play itself, a minimax versus a minimax. So we should always get a draw in a game of tic-tac-toe. And it took a few seconds to complete the game. I think it was somewhere around like 20 to 30, just depending on how our computer was feeling that day. And that's because when you have a 3x3 board, there are a total of the number of board spaces, so that's 9, factorial different moves that you can make, because you've got the first player can pick 9 different spaces, and then the next player can pick 8 of the remaining, and then 7 of the remaining, and 6 and 5 and 4, so you run a factorial, and you get over 300,000 moves, and our computer can handle that. But when we first tried to run this naive minimax on the 5x5 board, we said, hey, we got this working, let's just push it, let's just see what happens. We didn't see anything happen after a 32-hour run. So we're scratching our heads saying, okay, did we mess something up in the code, or what's going on here? And we sat down, did a 10 seconds of math, and realized that on a 5x5 board, we have 25 factorial moves, which is about 1.5 times 10 to the 25th. That's a lot. Even if minimax is being run in just a few seconds, or even less than seconds, we computed that it would take us somewhere around 1 times 10 to the 15 years to complete our game, which we don't have that kind of time. So we needed, we elevated this issue. We said, look, we got to alleviate what's going on here. We need to prune our search space down within the minimax in order to try to find an answer faster. If we wait, over 1 billion years to get a solution here, that's not going to be good enough. We need to implement something. So we decided to go ahead and implement our alpha beta pruning. If we don't have to call minimax as much, we should be better off. So we went and did that. We implemented alpha beta pruning. We tested it on the 3x3 because we knew we could work on that board. And we found that there were fewer calls to the minimax algorithm by a factor of about 16. And in doing this, we got an entirely faster computational time by a factor of 10. So if games were taking 20 to 30 seconds before just to run on the 3x3, they were now taking 2 to 3 seconds. So much faster. We really liked that. But even if we're faster by a factor of 10, we were still waiting, millions of billions of years before. And even if I were to make that faster by a factor of 10, we're still waiting billions of years. So it's still just too computationally expensive. The runtime is too long for a alpha beta pruning method to work by itself. And the simple reason to that is, even though you're implementing alpha beta pruning, you still need to get all the way down that search tree. You need to say, look, I've started up here with move number 1, and then there's move 2, 3, 4, 5, 6, 7, 8, 9. And this is for a simple 3x3 game. So you need to run through that, but this needs to take place 9 different or 8 more times whenever you get to the second one. And then these are each taking, many times. And this search tree is still giant. And even if you're pruning, you still had to go all the way down. And if you had a 5x5 board, you need to go all the way down to 25 down here. And for the 10x10 board, you're going 100 moves before you even find one possible solution so that you can begin your pruning process. And this is just too long of a runtime. And this is when we started to implement our first order logic of forced moves and our depth limited search. So in order to get away from this going all the way to the end here, we added the forced moves. And the idea with the forced move is, if you already have to play into a space to either win the game or prevent the game, we don't have to call miniMax anymore, which is great because now we don't run through this recursive application. We don't run through the algorithm, and we simply say, go. Like, you win here. Next player, go again. This could also help as the game goes on when it's, you go, I go, you go, I go, because all of our moves must block each other. So we thought, hey, if we maybe have to search halfway through a game within the miniMax algorithm, eventually at some point we'd get to the bottom of it, and whenever that would happen, we would just cycle it out. It was effective. It helped later on in the game, but it doesn't help at all early in the game because there's still multiple turns away from a win. You don't know where you're at. So this miniMax with alpha beta pruning, it's still being called and it's still running that whole depth of the tree. So we decided to implement a depth limited search. We simply said, look, we're going to allow you to search down 2 deep. So your depth limit is 2 or 3. So, you can only come down here. You can't go all the way down to 25. You're going to make your decision off the best thing you see here. And this is a bit of an issue here because whenever you're running the miniMax algorithm, you need to return back up the tree the value you get at the end leaf node. You need to return back a -1 for a minimizer or a +1 for a maximizer, or in a draw case, the 0 value. Like, you must return something. And that only occurred if a player won the game, if there was a win, lose, or a draw. And those only happen at the end once you have finished with the full depth of the tree for however long you need to go to get that win. We weren't doing that anymore. If we had a 5x5 board, you need at least 5 turns to win that game. You need 5 to go across a row, or 5 down a column, or 5 along a diagonal. If we're saying, yeah, you can only look 2 into the future, the miniMax algorithm is never going to find an end leaf node. So what we had to do is we had to implement a heuristic in order to say, look, we don't know what the end result of the game will be, but this will get you into a better place. If we follow this estimation on what is good and what is bad, this will allow you to make a justifiable decision and help you quickly make that decision moving forward. So we implemented a heuristic here. The way that heuristic actually was calculated, and maybe we can just show this on the next page. The heuristic was calculated in the following way. We took a board, so let's just pretend we have a 3x3 here because it's easy to work with. And let's just put an X up here and an O in the middle. What we decided to do for the heuristic was just to see how many open lines exist for each of the players. So this will be the X open lines, and this will be the O open lines. And the way we calculate or kind of formulate what an open line is we look at what we have here and we say, can the X player finish out this line to win? And if we take a look at this, X can win in 1. We can't win in the center, but we can win in the bottom, so that's 2. 3, we can't win in the middle. 4. So the X open has 4. If we do the same thing for the O player, well, the O player, it can't win vertically in this first column because the X is there. It can't win horizontally in the first column, but it can win 1, 2, 3, 4, and it can also win 5. So there's 5 ways that the O player can win. And then what we simply did for our heuristic is we said, look, the heuristic is equal to the X open spaces minus the O open spaces, and in this case, 4 minus 5 is -1. So if you are the minimizer or the maximizer, you can get a value off this. And if you continue to play spaces that block out your opponent's winning conditions, you can get to a point where, if your opponent is unable to have an open line, your opponent can no longer win. And if your opponent can't win, well, you're at least going to get a draw out of that game. So you can at least, say, let's just play it one more time. Let's go again, which is, moving you closer to that victory condition. Now, it might not be getting you a victory. It might not be doing that. It might just say, hey, if I can close out a line for them, that's worth more in the heuristic than actually winning. Assuming that win is a few moves away. if the move is next, then we'll just take that as a forced move condition. But if that move is a few moves away and it's beyond our depth, we might just say close out a line, even if the win is close, because we don't see that win yet. And that's actually something that we noticed, and we'll see in some of our test samples as we go forward. Now, in order to evaluate what we're doing here, we ran this in a few different ways. We evaluated the AI, so that miniMax algorithm with the alpha beta pruning and the depth limit of search and the forced moves. We had it play itself. And in this case, as we're going to see, all the tests were a draw. We also had the AI play against a random player. What we mean by a random player is, the player either went first or second, their eyes were closed, and they just picked a location randomly on the board. Of the remaining open locations, their pick was, random or pseudo-random, as a computer will generate. We tested this on the 3x3 simply in order to look at, what happens when we go deeper and deeper into our depth-limited search. And then we tested it on the 5x5, 6, 7, 8, 9, and 10x10 board, but at shallower depths, simply because at these larger and larger board positions, going deeper into the search was extremely time-intensive. So that's what we're going to look at right here. For our AI versus AI, we see in this case that there were no wins. The AI knew how to play itself. It always had those forced move conditions where if it saw that you were about to win, it would prevent it. There was nothing the AI could do, even on, larger depth limited search values that could kind of set it up for a win. The AI could always kind of, see through itself. And when we ran these for just 10 games on each of the test sets, we had ties each and every time. One of the things that you'll quickly notice looking at these values, though, is when we look at the number of spaces. So these are 3x3 boards. These are for 25. These are 5x5s. This is your 6x6. These should say 49 in here, but those are our 7x7s, 8x8s, 9x9, and 10x10s. You'll quickly notice that if you take a look, especially for the larger boards, between the first and the second depth limited search values, for a 7x7 board, the average game time was about 4 seconds when your depth limit was 1. When we went to a depth limit of 2, average game time was 2 minutes. Just like that. For our 10x10 board at a depth limit of 1, we're looking at 3 minutes a game. When we went to a depth limit of 2 for the AI playing the AI, we started looking 2.5 hours per game. So these larger runs here for the AI playing itself, they took forever. And the average number of calls to miniMax they were just ginormous. Here we're looking at much deeper times. The number of calls is just, it's through the roof here. We're getting much larger game times. It's only really feasible to run these when we're sitting at smaller sets here. And we can see that on a 6x6 board with a depth limit of 3, we're running very similar to a 7x7 at a depth limit of 2. We see 134 here and 134 here. So, the times are always something that we were keeping in the back of our minds, like, hey, how long can we run this? What can we actually do for, a reasonable trial? But it was very, pleasing to see that no matter what happened here, nobody was able to win. Everything came out to be a tie. Now, from this, we did see a few interesting things here. When we took a look at those run times for a depth limit search of 1, as the number of board spaces increased, so, we went from a 3x3 here, and then we went from 5, 6, 7, 8, 9, and then our 10x10, we quickly see that this graph is growing as a power there. So it's growing very rapidly. For DLS equals 2, for the depth limited search, we're going down another step. We see that same shape as we go up in size. But notice from these scales, we're looking from 200 runtime seconds, so, maybe 3 minutes here, to 10,000. So that's our 2.5 hour mark that we're running up here for these large values. So that was the main takeaway there. When we actually took a ratio of each of these pieces, so we compared the 10x10 to the 10x10, we saw that just going from a DLS2 to DLS1, or from a 1 to 2, it was about 50 times longer to run these games. This is almost linear, but we do see that there is some sort of shape in here, so we weren't exactly certain what to make of that. But it was very interesting to note that as we went up in board spaces, going to deeper and deeper depths, quickly started to scale up those run times. So it was something that made us a little nervous in terms of our runs later on, but it was just something to be mindful of, and it was an interesting feature that we found from these searches. If we just take a look at what miniMax does in and of itself, we looked at the average game time versus the average number of calls to miniMax. In some of our games, we had a ginormous call to miniMax, and we see that way out here. But a majority of our runs were a much smaller value. We kind of zoomed in on this blue box over here. This is our blue box side. And we see in this case, we have a very linear line here. That's simply because, on average, each miniMax call is taking approximately the same amount of time. So as we take more of them, we're just kind of scaling that time up linearly. There is some sort of overhead that this y-intercept represents. Maybe that's the calls to print functions to kind of display things to the board. There's some sort of overhead being dealt with there. But it is interesting to take a look at how these how it was miniMax was just kind of scaling linearly as the number of calls increased, and it happened from a very small segment in time to a very large segment as well. So it was nice to see there. Now we also ran all of our miniMax algorithm against the random player that I mentioned before. In doing this, we ran the random player as a first player and a second player, and we show that here. If the AI is going second, that means the random player is going first, and if the AI is going first, that means the random player went second. Looking at the result data here, we actually were only able to see wins occur for the random player on 3x3 boards, and then once on a 5x5 board right here, the kind of blemish in the whole scenario. This is a kind of interesting thing to see. And if we kind of look at the results down here, here's our 3x3 board with the AI playing second, and the second player in Tic-Tac-Toe is known to be at the disadvantage. If everybody's playing optimally, the best a second player can ever do is tie. And what ended up occurring, is just through feature chance, based on the depth limit of 1, 2, 3, 4, 5. When the depth limit is very shallow, our computer can't look that far ahead, and it did happen a few times that the random player was able to kind of win one over. It was able to place into a situation that allowed a victory for them. Once our depth limit went deep enough on the 3x3 board, we were unable to see that random player ever win again, which is kind of interesting. With the AI playing first, we see that first advantage. There were no games where the player was able to win for a depth limit of 1 and 2, which, before for those two depths, there were 7 and 5 player victories. In this case, our computer AI either won or it tied in, just randomness of the setup. So very nice to see that happening there. Whenever we ran this for largers, so here's our the AI going first at DLS equals 1, so a depth limit of search of 1. We see that we either have the computer win or a tie game. And as the depth limit stays at 1, but the number of board spaces increases, we actually see something interesting. We see that the computer win ratio, generally speaking, trends downward, and the tie game ratio, generally speaking, trends upward. And this happened both at DLS equal 1 and DLS equal 2. We can see here that we kind of get a trending downward. We saw a nice kind of anomalous spike there, but the number of tie games also looks like it goes up. And there's actually a reason for this. If you have a larger and larger board space, there are just more chances to have a line be closed off from you. And we can take a look at it like this. Here is a, what is this? 1, 2, 3, 4, 5, 6, a 7x7 board. And let's have our first player just try to run across the board, horizontally here. I take the first move, it's an X, and then randomly we'll just throw something somewhere else. And then we'll just say that 2, 3, 4, 5. You've got 5 more moves. Or here, let's just roll it back. So you randomly place there. I take my next move, it's here. You now, if you're the opposing player and you're playing randomly, you're just trying to hit one of these 5 out of whatever is remaining. Let's say you don't. You play up there. Well, when the next player goes, you're now just trying to hit these 4 out of whatever's remaining. And then the 3, and then the 2, and then the last one. you've got a lot of chances to get one of those spaces. And it actually turns out on a 10 by 10 board, the odds of a player, even if you're the opening player and you're trying to place into situations, the odds of the second player just randomly messing up your line, it's about 40%. It's like just under 40, which, oh boy, like that's pretty good odds, that you're not going to be able to finish a line just running across the board. And if that ends up happening, if you end up getting close and at the last second this player clogs it, well, they also have all these other random lines that have been closed off around the board. And now if you're trying to get a victory, where can you go? You can only go vertical. You can't do vertical, can't do vertical. You can do vertical, you can't. You can do vertical, closed, closed. You've got this line, closed, 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 closed. You can't do a diagonal. You can't do a diagonal. You only have 4 lines left. That's not a lot of options to get your win. So as boards get bigger, that random player is allowed to just play around the board and kind of, clutter the board, mess things up, really make it gunky. And at the last second, if they just happen to block it or if they happen to block it in the middle, they've still closed a lot of things off for that AI trying to win the game. So that's generally why we see this go down. On the 3x3 board, we don't see that as much because on a 3x3 board, we don't have to look very far ahead. And if our AI goes here, as soon as that second player makes a mistake, we can quickly close this game off. The AI can immediately say like, hey, we're just going to make that next move, and then boom, boom, we're done. We've made the victory. So it's kind of an interesting thing to see. As that board space gets bigger, it's just harder to actually make a win. So kind of neat feature there. We see something similar whenever our AI goes second. We see less victories simply because you're the second player, or our AI is the second player. It's harder to win there. You're at the disadvantage. So we see lower win ratios, higher tie ratios, and we once again see this kind of downward trend in the wins and the somewhat upward trends in ties for both a depth limit of 1 and a depth limit of 2. And it's very evident over here that we see this. So very interesting feature that came out of that. In terms of some of the limitations, known issues, and future improvements for our code, it's known that our runtimes are just long. This is a 8x8 board here on the left at a depth limit of 2, and this is just the 14th move, and it's taken 34 seconds to make it. It takes a long time to make these moves. For the 10x10, we're looking right here. What is that? 4 minutes to make a move, just for the 8th move here. So it takes a long time to make these moves. We need to be able to do this faster. One of the methods that we thought about but ended up not implementing was, instead of just using a depth limited search, using a iterative depth limited search, so that we go down the tree some distance, and when we hit maybe like 15 seconds or so, something that we think is long enough, we cut the code, say, use your heuristic, make a result, and then we hold that and continue to look down branches as the game progresses. This would just allow us to kind of store spaces and store the board a bit, but we didn't really kind of want to go down that path right here. We weren't exactly certain in terms of what kind of implementation to use there, so we kept it as just a traditional depth limited search instead of the iterative method. We also originally, as was mentioned, had a generalized win condition. If you're playing on a 6x6 board, what happens if you get 3 in a row? How can you play that game? And one of the reasons we didn't do that was simply in this scenario here. If we take a look at this, X is the first player. They've gone twice on a 1, 2, 3, 4, 5x5 board, and O went here. At this point, it's O's turn to go again, and can you figure out where O needs to go to prevent them from getting 3 in a row? Well, if O goes here, then X goes to this side. If O went here, then X plays to the back. So we kind of get this trivial case, and one of the kind of interesting things about this is, while this is trivial to kind of put out here, our miniMax would have never really found it, because the depth limit to get down here and C, so there's move 1, and then there's move 2, and then there's move 3, and then 4. That depth limit is just too deep. It's like 4 or 5 in order to win that, and we were ending our depth limit at 2. So this wouldn't have been seen anyways from what we did, and it's semi-trivial in this case. It might be interesting to do something like this if you have a awkwardly shaped board, maybe a rectangle, or maybe if you were to design something like this, like an H, and said, hey, get 6 in a row via this, like that might be interesting. But for what we did, square boards, this just wasn't something we looked at. There was one other thing we actually did here. While we did have the generalized win conditions set up, we opted eventually to just go for hard-coded win conditions. And the reason we did this is that when we set up the generalized win conditions for any size board and any number to win, you actually had to search that entire board for these sublines to win, and it took a long time. When we hard-coded win conditions in, we found that they were being run twice as fast as the generalized version. And we also needed those hard-coded versions in order to calculate the open lines for the heuristic. So it was very useful to actually hard-code things in here. It just made it a less generalized case, which, pros and cons to that. We also recognize that it is a little annoying, given the fact that our depth was so low, that we'd get to scenarios where the board would be, seen to be a victory, but the computer, the AI, wouldn't find it. So if you look at this here, we've got O running down this main forward diagonal, and all it needs to take is 6-6 and 7-7 and win. And instead what ends up happening is the computer, it starts taking these going across until the random player boxes them out. And then it says, okay, well, I'll start going across here. It could have taken 6-6 and 7-7 much earlier in that decision process. But the reason why these aren't being found very early is because the way our miniMax is being run is it's being run going across the rows. And as a result of heuristic, these just aren't being seen as opportune ways to win the game. So a way to kind of solve this is instead of running, across the rows and then down and then across the row and then down, as we go through miniMax and then prune, we should be doing this randomly, where instead of saying we're starting at the top and going over, we're just saying, I'm going to look at this position and run a little miniMax tree on that. And then I'm going to look at this position and run a little miniMax tree on that. And then I'm going to look at this one and run a little miniMax on that. And what that does is it gives the board more space to look over, and it doesn't get caught in this upper area of the tic-tac-toe board. So that could actually save us a lot of time there, considering, especially because the X player here is moving randomly, it might be better off to kind of make our own search trees in a random nature to kind of exploit that and try to find something that might have been buried, like this really easy win condition that could have saved so much time within our runs. Two other things to look at. Counting the number of tie games. This was a little interesting. We were outputting the number of tie games we had and the number of wins and losses to just a text file. And early on, when we were running 10 by 10s, we found exactly 10 total games being run here. And we were running for larger values. We found that as well. But it started to be that later on when we were running like 500 for larger board sets. We were getting not 500 as our total games run when we summed these together. If you do 423 and 31, you're getting 454. What happened to your other 46 games? We think what was happening here is that the tie game counts were tucked under one of the ending conditions, and depending on which player was ending the game on a tie, this would come out to be hidden every once in a while. So this wasn't a huge issue. It's kind of perplexing why that happened, because it didn't happen on the 3x3 board, but it did happen on larger ones, 5x5 up to the 10x10. But what we were able to do here is we knew that the player couldn't win in these random scenarios based off of the method the game is being played in and how easy it is for that forced move to just close them off. So we simply said, look, if we're missing moves out of here, they're just tie games. We can't count them as wins. They're just tie games. Somehow we're losing the tie games there. All the wins are coming back correctly. The ties are just being weird. And then the last thing that was a little, I don't know, maybe not 2022, but more 1993, was we don't have a super friendly GUI. It would be nice to display something to the user to have them click on what board they want, but we don't have that kind of background within Python. So we kind of have more of a terminal window where, would you like to play Tic-Tac-Topia? And if you say yes, you can select what kind of board you'd like to play on, and we can play on a 3x3 board. And here's our little board here. And would we like to play first? Of course we would. So we'll go ahead and play. And we simply enter our row 0, and then what's our column 0. And then we've played as the X position. The computer's played the O position. We see the calls to miniMax and the runtime because we find that interesting. And then we just continue to play. I'll play in 1, 0. The computer is played in the bottom because that's a forced move. It's blocked me off. And then I now need to play up here into 0, 2, or else I'm going to allow the computer to win. But let's just see the computer win. It's always nice to do that. So I will misplay. The computer's played this easy win. Computer has won. Long live the AI. And if we'd like to play again, we can. So while it's not super slick and savvy and point and click based, it is still easy enough to kind of walk through and play the game until you want. It's nice enough to do what we need to do there, and it does. It's kind of got a retro feel to it, so I don't hate it. But that was our game. That was the whole Tic-Tac-Topia, Tic-Tac-Toe land for 3x3s, 5, 6, 7, 8, 9, and 10x10s. I hope you kind of enjoyed this walkthrough of what we did and kind of some of our struggles as we were coding this and our ways that we found around them. miniMax itself wasn't enough here. We had to start looking at pruning and depth limited searches and using that first order logic to make forced moves. But through all of it, we got a working product out, and it runs really well, and we're really happy with it. So hope you enjoyed this. If you have any questions, feel free to reach out to us at any time, and we'll be happy to get back to you. So until then, thank you very much, and have a wonderful day or afternoon or morning, wherever you're at. Adios.